Imagine a star so vast that, if placed where the Sun is, it could stretch far beyond the inner planets and deep into the solar system. From Earth, it appears as only a faint point of light, almost lost in the darkness of the Milky Way. But hidden inside that tiny glow may be the largest star we've ever found. Tonight, the journey moves from the quiet night sky to one of the most enormous objects known in the universe. If this kind of deep space story belongs on the channel, please like the video, subscribe, and settle in. Above Earth, the night sky appears as a dark field marked by points of light, faint hazes, and broad bands of deeper shadow. In that wide visible scene, the largest star ever found does not announce itself as the largest thing in view. It does not rise above all others in obvious scale. It does not fill the sky or stand apart in a way that the eye can easily grasp. It arrives only as a distant star among many distant stars, placed so far away that even an object of immense size is reduced to a small point of light. This is the first condition of the subject. The greatest known stars belong first to distance, and only after that to size. From the ground, the sky gives no direct sense of how large a star truly is. Human sight gathers light, colour, and position, but it does not reveal the width of a distant star in any ordinary way. A nearby lamp can look brighter than a mountain fire far away. In much the same manner, a bright star can seem important because it is close, while a far more enormous star can remain dim, softened by dust, distance, and the limits of the eye. The sky therefore presents stars as appearances rather than as bodies. It offers a pattern of light, not a map of physical size. On the clearest nights, away from city light, the Milky Way stretches as a pale band across the darkness. It looks soft, almost cloud-like, yet it is made of many stars whose light blends together before reaching the eye. Dark lanes cross it in places where dust blocks the glow from more distant regions. Brighter zones gather toward the crowded inner parts of the galaxy. Fainter regions thin outward. In this broad river of starlight, the eye meets only the surface impression of a far larger structure. The Milky Way seen from Earth is not the whole galaxy laid open in detail. It is the visible trace of a stellar system so large that light takes about 100,000 years to cross much of it. Within that system, stars differ greatly from one another. Some are small, cool, and faint, and they spend extremely long spans of time changing only slowly. Others are larger, hotter, and more luminous, pouring energy into space at much higher rates. A few become so expanded in late life that their outer layers swell to extraordinary size. These are the stars that matter here. They are not the most common stars in the galaxy. They are rare, short-lived by stellar standards, and difficult to understand fully because they change, lose matter, and sit at great distances. Yet from Earth, they still enter awareness in the simplest possible form, as part of the same silent field of night. The largest known stars are measured not by how bright they seem in the sky, but by their physical extent, especially the radius from the center out to the visible outer layers. In common language, radius means the distance from the middle of a sphere to its surface. For a star, even this needs care. A star does not have a hard surface like stone or metal. Its outer layers thin gradually into space. Observations indicate that astronomers define a practical visible boundary based on the depth from which most of the light escapes. This means that stellar size is not a matter of touching an edge. It is a matter of interpreting light from a glowing gas sphere whose boundary is real in one sense and diffuse in another. From the ground, such ideas remain hidden. A star that appears steady and modest can in fact be hundreds or even more than 1,000 times wider than the Sun. If one of the most extreme giant stars were placed where the Sun now is, its outer layers would extend far beyond the orbits of the inner planets. In some estimates for the largest candidates, the swollen envelope would reach outward to the region of Jupiter, or even farther, depending on the model and the exact way the boundary is defined. These comparisons help the mind, but the sky itself does not reveal them. The sky remains calm, flat in appearance, and silent about the true scale behind its points of light. The Sun, seen by day, gives a false sense of what stars are usually like. It seems dominant because it is near, and because all other stars are immensely farther away. Yet the Sun is not among the largest stars. It is a main sequence star, meaning a star in the long stable stage of life, during which hydrogen in the core is fused into helium. That steady central burning supports the star against gravity. Many stars spend most of their lives in that condition. The largest known stars are not in that calm stage. They belong to a later and less stable part of stellar life, after deep internal changes have altered the balance between gravity and outward pressure. Their vast size is not a permanent condition. It is part of an evolved state. Seen from Earth, the search for the largest star begins with patience rather than spectacle. A star must first be noticed, catalogued, compared, and placed in relation to many others. Its position in the sky matters because certain directions look through richer parts of the Milky Way, where giant stars are more likely to be found. Dust also matters because dust dims and reddens starlight, making distant objects harder to judge. The eye alone cannot separate a truly red giant star from a less remarkable star seen through thick dust. What appears simple in the sky often hides layers of complexity between Earth and the source of light. This outermost region of the subject is therefore not the star itself, but the human vantage point. Earth sits inside the Milky Way rather than outside it. Observation begins from within a crowded stellar disk, looking through gas, dust, and overlapping lines of sight. The night sky is not a clear museum display. It is more like a deep forest seen from inside, where near branches, distant trunks, and patches of light overlap. In that condition, size must be inferred, distance must be estimated, light must be corrected for what happens along the way. Only then can a star that looks ordinary begin to emerge as something extreme. For now, the largest known star remains only a possibility hidden inside the quiet appearance of the sky. It belongs to a galaxy full of stars, and to a human viewpoint that sees almost all of them as points. The first layer of understanding is simply, this greatness in the universe is often invisible at first glance. The night sky does not display scale openly. It presents only light arriving from far away, and within that light, the largest star ever found waits to be recognized. The night sky gives only a surface impression, but beyond that impression lies the Milky Way, the larger setting in which the greatest known stars exist. The galaxy is a vast rotating system of stars, gas, dust, and dark matter held together by gravity. Its visible form is that of a spiral galaxy, with a broad disk, a central bullroad of older stars, and curved arms that wind through the disk like luminous lanes. Earth rests within that disk rather than above it, so the galaxy is not seen from the outside as a complete shape. It is experienced from within, through crowded directions, obscured distances, and long paths of light passing through many layers of matter. The disk of the Milky Way stretches across more than 100,000 light-years. It is thin compared with its width, though not truly flat. Stars move through it on long orbits around the galactic center. The Sun takes about 240 million years to complete one such orbit. This motion is steady and immense, but the galaxy does not turn like a rigid wheel. Inner parts and outer parts move differently, and the stars of the disk trace their own long courses through a shared gravitational structure. In this broad rotating system, the largest stars are only brief and local features, but they still depend strongly on where in the galaxy they are born and where they spend their short lives. The Milky Way is not uniform from one region to another. Some areas are rich in gas and dust, some are crowded with young stars, some hold mostly older stars, with less raw material for new stellar birth. Spiral arms matter here because they are places where gas and dust gather more strongly than in many regions between the arms. They are not fixed solid structures made of the same stars forever. They are better understood as patterns of higher density moving through the disk, shaping where clouds become compressed and where star formation becomes more active. In these denser lanes, the ingredients for large and luminous stars are more often found. From Earth, one of the strongest impressions of the Milky Way is the dark division that cuts through parts of its glowing band. These dark lanes are not empty regions. They are full of dust, made of tiny solid grains mixed with gas. Dust blocks and scatters visible light. A region crowded with stars can therefore appear dim, or even hidden if thick dust lies in front of it. This has deep importance for the search for extreme stars. The most massive and swollen stars are often linked to regions rich in gas and dust, yet those same materials can veil them from ordinary view. A star may be intrinsically very luminous, and still remain difficult to study because its light reaches Earth only after passing through obscuring layers. The inner parts of the galaxy are especially crowded and dust-rich. Toward the center, stars become more densely packed, and the view along the disk crosses many overlapping structures at different distances. The central bulge contains a great concentration of older stars, while the surrounding inner disk holds active and complex regions where gas clouds, clusters, and luminous young populations share space. The farther one looks through the galactic plane, the more difficult it becomes to separate one region from another. A bright star might lie relatively nearby, while a dimmer point in the same direction could in fact be vastly more luminous, but much farther away and heavily reddened by dust. This reddening is one of the quiet signatures of the galaxy's structure. Dust tends to scatter blue light more effectively than red light, so starlight passing through dusty regions often arrives looking redder than it truly is at the source. That effect can make a hot star appear less blue, or help a distant red star appear even deeper in color. To understand a star within the Milky Way, astronomers must therefore untangle the imprint of the galaxy itself from the light of the star. The galaxy does not simply contain stars, it modifies how they are seen. Gas is just as important as dust. Much of the star-forming gas in the Milky Way exists in large cold clouds, especially in the disk and along spiral arms. These clouds can span great distances and contain enough mass to form many stars. Within them, denser parts can collapse under gravity. The larger stars require especially rich and dense birthplaces, because massive stars consume fuel quickly and form under more demanding conditions than smaller stars. The Milky Way provides such places, but not evenly. It offers pockets of opportunity, concentrated in certain regions where the balance of gas, pressure, turbulence, and gravity allows rare stellar extremes to emerge. The disk also carries a gradient in chemical richness. Stars born later in the history of the galaxy often form from material already enriched by earlier generations of stars. Elements heavier than hydrogen and helium, produced in stellar interiors and returned to space, become part of later gas clouds. This matters because the lives of massive stars depend not only on mass but also on composition. Their winds, brightness, and outer layers are influenced by the elements mixed through their gas. The Milky Way is therefore not merely a backdrop. It is a physical environment that shapes how giant stars form, how they evolve, and how they shed matter. Above and below the disk lies the halo, a more diffuse region containing older stars and globular clusters. It is part of the galaxy, but it is not the primary home of the larger swollen stars. Those stars belong much more strongly to the active disk, where gas remains abundant. The contrast is useful. The halo speaks of age and relative quiet. The star-rich disk, especially along its denser lanes, speaks of ongoing transformation. The greatest stars are creatures of that transforming environment. From the human viewpoint inside the disk, the Milky Way is both home and obstacle. It supplies the regions where extreme stars can exist, yet it also complicates every attempt to measure them. Distance becomes uncertain. Dust alters colour and brightness. Crowded sightlines cause confusion. Still, the general setting is clear. The larger stars known do not appear randomly across the galaxy. They are associated with the richer and more active portions of the stellar disk, where dust-darkened spiral regions hold both the raw material and the clustered companionship that massive stars require. Within this galactic structure, the subject narrows. The larger stars are not simply large objects floating in emptiness. They belong to the Milky Way's busy interior, to its gas-laden arms, to its obscured stellar lanes, and to the rare environments where matter gathers densely enough to build such brief and enormous forms. Within the Milky Way, the larger stars do not emerge from ordinary empty space. They begin in giant molecular clouds, the cold and dense regions where gas and dust gather on a vast scale. These clouds are among the darkest visible structures in the galaxy when seen against bright star fields, because the dust within them blocks background light. Yet their darkness is not a sign of absence. It is a sign of material so thick and widespread that it hides what lies beyond. In these regions, the next layer inward begins, not at the surface of a star, but at the place where such a star first becomes possible. A giant molecular cloud is made mostly of hydrogen in molecular form, meaning pairs of hydrogen atoms bound together. Helium is also present, along with smaller amounts of heavier elements and tiny solid dust grains. The temperatures inside much of the cloud are low by everyday standards, often only a few tens of degrees above absolute zero. At such temperatures, gas moves slowly enough for gravity to gain influence in denser pockets. The cloud does not collapse all at once into one object. It fragments. Some parts remain diffuse, some become filaments, long thread-like structures shaped by turbulence, gravity, magnetic fields, and pressure. Some knots within those filaments grow dense enough to contract further. In these denser knots, stars begin. The birthplaces of very large stars are not usually quiet or isolated. Observations indicate that massive stars form in the richest and densest parts of star-forming complexes, where much matter is concentrated within comparatively small regions. The surrounding cloud is not smooth. It is structured, stirred, and uneven. Motion runs through it at many scales. Gas streams, collides, compresses, and disperses. Turbulence, meaning irregular and chaotic motion in a fluid, helps shape the cloud into denser and thinner regions. Gravity then acts most strongly where density has already increased. The cloud becomes a landscape of possible collapse, not a simple sphere falling inward. As a dense region contracts, gravitational energy is converted into heat. The material in the center grows warmer and more compressed. At first, this object is not yet a true star. It is a protostar, an early forming body still drawing in matter from the cloud around it. Gas falls inward, but not always directly. Because the collapsing material carries angular momentum, meaning the tendency of rotating matter to keep rotating, some of it settles into a disk around the growing center. Jets and outflows can appear along the rotation axis, helping carry away some angular momentum and allowing more material to continue falling inward. Even at this stage, the environment of a forming star is active and shaped by motion rather than stillness. For stars of moderate size, this process is already complex. For the most massive stars, it becomes even more difficult. A forming massive star grows bright very quickly. That brightness pushes outward on nearby gas and dust through radiation pressure, the force carried by light. In simple terms, the forming star begins to resist the very inflow that is helping to build it. For a time, this raised a basic problem in stellar theory. If a growing star becomes bright enough to push material away, how can it continue gaining? Mass observations and models now indicate that the answer lies in geometry, density, and flow. Matter can still reach the star through dense accretion streams and disks, while radiation escapes more easily in other directions. The growth is not gentle or perfectly balanced, but it can continue. Large stars therefore require more than just a large amount of gas. They require a cloud environment able to deliver matter rapidly before feedback becomes too strong. Feedback is the influence a forming star has on the material around it through light, heat, winds, and later ionizing radiation. In the case of massive stars, feedback becomes powerful early. Their ultraviolet light ionizes surrounding hydrogen, stripping electrons from atoms and creating glowing regions of hot gas. Their winds can push and disturb nearby matter. These effects can halt star formation in some places while compressing gas elsewhere. A stellar nursery is therefore not merely a place of birth. It is also a place of interruption, erosion, and rearrangement. Because of this, the largest stars are rare. Most of the gas in a giant molecular cloud does not become one extreme star. Much of it forms smaller stars. Some remains in the cloud. Some is driven away. A cloud may contain enough mass to build many stars, but only a very small fraction reach the highest masses. The probability is low, and the requirements are strict. The region must be rich in gas, dense enough to support rapid inflow, and active enough to gather matter into the deepest collapsing centers. Even then, the result may be brief. Massive stars use energy quickly and begin altering their surroundings almost as soon as they form. Dust in the natal cloud plays a quiet but essential role. It helps cool gas by radiating energy away, and cooling allows collapse to proceed more effectively in many cases. Dust also shields deeper regions from external radiation, preserving cold and dense conditions. At the same time, dust hides the earlier stages of massive star birth from ordinary visible light. Much of what is known about stellar nurseries comes from infrared and radio observations, which can pass through dust more effectively than visible light. The larger stars begin in places that are often almost invisible in ordinary starlight. Within a giant molecular cloud, star formation often occurs in groups rather than in isolation. Dense regions can give rise to many stars within the same general volume. This matters because the larger stars are commonly associated with clustered birth. The cloud does not produce one giant object alone in an otherwise empty region. It produces a family of stars of different masses, ages, and brightnesses, sharing a common origin in the same cloud structure. The very largest among them are part of that crowded beginning. Their formation is linked to abundance, not solitude. These nurseries are short-lived compared with the age of the galaxy. Massive stars form, shine, and disturb their surroundings on relatively short timescales. The cloud that made them is changed by their presence. Gas is heated, dust is moved. Nearby dense pockets may either collapse more strongly or be torn apart. The nursery evolves rapidly. What begins as a dark and cold cloud becomes, in time, a region of light, wind, and exposed young stars. At this layer of the story, the largest known stars are still not visible as mature giants. They exist only as possibilities inside dense and cold clouds. Their future size is not yet written in swollen outer layers, red colour, or immense radius. It lies in the special conditions of the nursery itself, where gravity, gas, dust, turbulence, and time briefly combine in the rare way required to begin building one of the greatest stellar bodies the galaxy can produce. Inside the great dark clouds of the Milky Way, star formation rarely proceeds one star at a time in complete isolation. It more often produces groups, associations, and compact clusters, where many stars emerge from the same reservoir of gas within a relatively limited region of space. For the largest stars, this clustered setting is especially important. Their birth depends on unusually rich conditions, and such conditions tend to occur where matter is concentrated strongly enough to form not just one star, but many. The next inward layer of the story therefore enters the young massive cluster, the crowded stellar environment in which some of the galaxy's most remarkable stars begin their brief lives. A star cluster is a group of stars that share a common origin in the same cloud. In a young cluster, the stars are born at roughly the same time on astronomical scales, though not always at precisely the same moment. They begin close together, with a common age range, similar initial chemical composition, and a shared birthplace in the gas and dust of a stellar nursery. A massive cluster contains enough material to produce many bright and short-lived stars, including the rare high-mass stars that later evolve into supergiants. Such a cluster does not remain embedded forever. As its stars begin to shine and blow winds into the surrounding cloud, the gas and dust are reshaped, heated, and in many places driven outward. Over time, the cluster becomes more visible as the veil around it thins. The appearance of a young massive cluster is very different from the still darkness of a molecular cloud. Instead of an obscuring mass with only hidden activity inside, the cluster becomes a bright concentration of stars packed more closely together than the stars in the Sun's neighbourhood. The highest mass members dominate the light. They are luminous, hot in their early stages, and powerful in their influence on their surroundings. Their radiation ionizes nearby gas. Their winds carve cavities and stir the local medium. In the earliest period, they shape the environment even before the cluster settles into a more exposed and recognizable form. The largest stars known are tied to this kind of setting, because such stars are not only rare but also short-lived. A short-lived star cannot drift very far from its birthplace before reaching a later stage of evolution. If an enormous evolved star is seen today, there is a strong chance that it still lies near the cluster or association where it formed, or at least within the same broad star-forming complex. Observations of red supergiants in young clusters support this pattern. These stars are evolved, meaning they have already passed beyond the stable central hydrogen-burning stage, but they are not ancient. They still belong to populations young enough that many neighbouring stars can reveal the shared age of the system. A cluster helps astronomers because it provides context. A single distant star is difficult to judge on its own. Its brightness depends on distance. its colour is altered by dust. Its stage of life may be uncertain without careful measurement, but a group of stars born together offers a comparative framework. By examining the full stellar population of a cluster, astronomers can estimate the age of the system and infer what kinds of stars should be present at that age. In a young massive cluster, the most massive stars evolve quickly. Some remain hot and blue, some become Wolf-Rayet stars, a class of hot evolved stars with strong stellar winds. Some enter the red supergiant stage, becoming cooler, larger, and redder. The mixture of such stars provides a clock of sorts, not exact, but useful. This matters deeply for the search for the largest known stars. Extreme red supergiants do not appear in random isolation without context. They are often found in or near clusters rich enough to have formed very massive stars in the first place. Their presence tells something about the age of the cluster, and the cluster in turn helps constrain the properties of the star. If a star appears to be an enormous red supergiant, but it sits in a population whose age would not plausibly produce such an object, then the interpretation must be questioned. The cluster therefore acts as an environment of both origin and verification. Young massive clusters are not calm. Their stars interact through radiation, winds, and gravity, and the cluster evolves rapidly compared with older, looser stellar populations. The most massive stars exhaust their central hydrogen quickly. In only a few million years, some begin to leave the stable main sequence and expand. Others lose mass through strong winds. The cluster changes in visible character as these luminous members evolve. A place once dominated by hot blue stars may come to include very bright red stars whose outer layers have swollen to extraordinary sizes. This transformation is one of the reasons clusters containing red supergiants are so valuable. They represent a narrow and revealing stage in the life of a massive stellar population. The stars in a cluster do not all have the same mass. Most are smaller and fainter than the rare giants that later draw attention. Yet the presence of many lesser stars is part of what makes the cluster physically meaningful. A cluster is not a decorative background around one remarkable object. It is the full outcome of a shared birth event. The great star and the modest star are siblings of the same cloud, shaped by the same general environment but separated by differences in mass that lead to very different fates. The larger the initial mass of a star, the faster it tends to live. This is why the most massive cluster members become evolved giants, while many smaller companions remain in much earlier stages of stellar life. Crowding is one of the defining features of these clusters. Near their centers, stars can be packed close enough that their light overlaps strongly in distant observations. Dust often remains significant as well, especially in clusters located in the richer inner parts of the Milky Way. This can make interpretation difficult. Even so, the general pattern is clear. The largest candidate stars emerge from regions where many stars form together, and where the total mass of the original cloud was high enough to support rare stellar extremes. Such clusters are temporary forms, over longer timescales, gravitational interactions, gas loss, and the deaths of massive members alter their structure. Some remain bound for long periods, others disperse more readily into the general disk of the galaxy. But during the relevant interval for red supergiants, the cluster still preserves the signature of common origin. It holds the stellar family together long enough for astronomers to read its age and nature. At this stage, the subject has moved inward from the galactic disk and dark stellar nursery into the bright communal environment where the future giant is no longer only a forming possibility. It is now one member of a youthful and crowded population, growing and changing among many nearby companions. The largest stars belong to abundance first, and individuality only afterward. Within a young massive cluster, the future giant is surrounded by many stars that share its birthplace. Yet not every bright red star in such a field proves to be one of the most extreme objects in the galaxy. Before astronomers can speak of the largest known star, they must first identify which stars are genuine candidates. That work begins not with size directly, because size cannot usually be seen, but with observation of light. The search for extremes is a discipline of careful sorting. It depends on brightness, colour, spectrum, distance, and the larger setting in which a star is found. Each of these offers part of the answer, and none is sufficient alone. The first clue is often brightness, but brightness in the sky is only apparent brightness, meaning how much light reaches Earth. A star can appear bright because it is close, not because it is especially powerful. Another star can appear modest because it is far away or hidden behind dust, even if it is producing vastly more energy. To compare stars fairly, astronomers seek intrinsic brightness, the true energy output of the star rather than the reduced amount received at Earth. This requires a distance estimate and a correction for light lost or altered along the way. The search for the largest stars is therefore never a simple ranking by what seems brightest in the sky. Colour is another clue. A red supergiant candidate usually appears red or reddish in suitable observations because its visible outer layers are relatively cool compared with hotter blue or white stars. In stellar language, cool does not mean cold in an ordinary sense. It means cooler than many other stars, while still remaining thousands of degrees above the temperatures of everyday objects. A cool star emits more of its visible light toward the red part of the spectrum than a hot star does. Yet colour alone can mislead. Dust between Earth and the star can make starlight look redder than it truly is. A distant star viewed through heavy dust can imitate some of the colour signature of a genuine red supergiant. The eye, and even a camera, cannot settle the matter by colour alone. This is where the spectrum becomes essential. A spectrum is the spread of a star's light into its component wavelengths, revealing a pattern of absorption and emission features tied to temperature, surface conditions, and chemical composition. In practice, the spectrum acts like a physical signature. For red supergiants, it shows lines and molecular bands consistent with cool and extended atmospheres. It can also help distinguish a true supergiant from a giant star of lower luminosity, or from other cool stars that only resemble it at first glance. Surface gravity is one of the key differences. In a red supergiant, the outer layers are spread over a much larger volume, so the surface gravity is lower than in smaller stars. That lower gravity leaves subtle marks in the spectrum, allowing astronomers to classify the star more reliably. Infrared observation is especially useful in this work, because many extreme red stars lie in dusty regions of the Milky Way. Visible light may be heavily dimmed before it reaches Earth. Infrared light can pass through dust more effectively, making hidden stars easier to detect. A star that is difficult to judge in ordinary visible wavelengths may stand out more clearly in infrared surveys. This is one reason why the census of red supergiants has improved with better infrared mapping of the galaxy. Dust does not disappear in the infrared, but its obscuring effect is reduced enough to reveal populations of cool, luminous stars that would otherwise remain difficult to study. Even after a star is identified as a likely red supergiant, the question of size remains indirect. Astronomers do not usually resolve the visible disk of such distant stars in ordinary observations. Instead, they infer size from a combination of luminosity and effective temperature. Effective temperature means the temperature a star would have if it radiated like an ideal thermal emitter, with the same total output. If the total luminosity is known, and the effective temperature is estimated from the spectrum, then the radius can be calculated. A more luminous star with the same temperature must be larger. A cooler star with the same luminosity must also be larger. The great radius of a red supergiant therefore emerges from the relation between how much energy the star emits and how cool its visible outer layers are. Distance is often the most difficult part of this chain. A small error in distance changes the inferred luminosity, and the inferred luminosity changes the inferred radius. In the crowded and dust-rich directions of the Milky Way where many extreme stars are found, distance can be especially uncertain. A star may seem associated with a cluster, but not truly belong to it. Another may belong, but the cluster distance itself may carry a significant margin of error. Because of this, the title of largest known star is rarely absolute in a simple sense. It depends on the best available measurements and on how uncertainties are handled. Variability adds another layer. Many red supergiants are variable stars, meaning their brightness changes over time. These changes are often not sudden in a dramatic sense, but they matter to measurement. A star observed in one season may appear somewhat different in output or color from the same star observed later. The outer layers of such stars are dynamic, and the dust around them can also change the light that escapes. To identify an extreme star properly, astronomers often need repeated observations rather than a single snapshot. The surrounding stellar population remains important as well. A candidate extreme star is stronger as a case when it sits within a cluster or association whose age and character match the expected life stage of a massive evolved star. Context supports identification. It helps separate a true member of a young massive population from an unrelated foreground or background star seen along the same line of sight. In this way, the search for extremes returns again to the group. One star becomes understandable through the company it keeps. By the end of this stage, the largest known stars are still not known as simple visible objects with directly measured edges. They are assembled through evidence, a red color corrected for dust, a spectrum consistent with a cool supergiant, an infrared brightness that survives obscuration, a distance tied to a cluster or other measurement, and a derived luminosity large enough to imply an extraordinary radius all combine into a candidate. Only then does a distant point of light begin to stand among the most immense stars known in the galaxy. Among the many regions of the Milky Way that contain massive stars, one obscured cluster has become especially important in the search for the largest known star. This is Stephenson II, a young and heavily reddened stellar cluster lying deep in the rich inner part of the galactic disk. It is not a place that stands out to ordinary sight. Its stars are dimmed and altered by the long path their light must cross before reaching Earth. Dust lies across the line of sight, softening the cluster's visible presence and making its members difficult to study in ordinary light. Yet behind that obscuration, Stephenson II has revealed one of the richest known gatherings of red supergiants in the Milky Way. The cluster lies in the direction of the inner galaxy, near the complex region where the scutum direction becomes especially crowded with stars, dust, and overlapping structures. This is one of the busiest sightlines in the Milky Way. Looking toward it from Earth means looking through the galactic plane, where gas and dust are abundant and where many stellar populations sit at different distances along nearly the same apparent line. The field is therefore not simple. A star seen in this direction is not easily assigned to one physical group without careful measurement. Stephenson II exists within this confusion, and much of its scientific importance comes from the fact that it can still be recognized as a real and coherent cluster despite the difficulty of the view. Its obscuration is central to its character. The cluster is heavily reddened, meaning that dust between Earth and the cluster removes more blue light than red light. This causes the stars to appear much redder and fainter, in visible wavelengths than they would if seen through a clear path. The cluster is therefore better studied in the infrared, where dust has a weaker effect. Infrared surveys have been crucial in revealing the luminous, cool stars that define Stephenson 2. Without that window, much of the cluster's significance would remain hidden behind the dust of the inner Milky Way. What makes Stephenson 2 remarkable is not only that it contains red supergiants, but that it contains many of them. Red supergiants are already rare as a class, because they represent a brief late stage in the lives of massive stars. To find a large concentration of them in one cluster means the cluster itself must be both young and initially very massive. The stars must have formed within a narrow enough range of time that several of the most massive members have now reached the red supergiant phase together. This makes Stephenson 2 a natural laboratory for the study of extreme stellar evolution. It preserves not one exceptional object alone, but an entire population of related evolved stars within a shared environment. The cluster does not sit in isolation as a single island of massive stars surrounded by emptiness. Observations indicate a broader concentration of red supergiants in the surrounding region, suggesting that Stephenson 2 may be part of a larger star-forming structure or a wider complex of massive stellar populations. This wider setting matters because it complicates membership. A luminous red star near the cluster on the sky may or may not belong to the central cluster itself. Some stars may be part of the same larger regional population without being tightly bound members of the core cluster. Others may lie at different distances along the same crowded line of sight. In such a region, association must be tested rather than assumed. Stephenson 218, the star often discussed as the leading candidate for the largest known star, is linked to this hidden environment. Its importance comes not only from its inferred size, but from its placement within the Stephenson 2 region, where a rich red supergiant population gives context to its evolutionary state. The cluster and its surroundings provide the age framework and stellar companionship that make such an interpretation plausible. A distant red star by itself might remain uncertain in status. A distant red star in a cluster rich with similar evolved massive stars becomes much more physically understandable. The distance to Stephenson 2 is large enough that its members remain unresolved as ordinary points of light in most observations, yet close enough in galactic terms to be studied with modern instruments. Even so, the exact distance has carried uncertainty, and that uncertainty affects all later conclusions about luminosity and radius. This is one reason why the title of largest known star remains a matter of measured inference, rather than direct visual certainty. The cluster gives a framework, but it does not erase every difficulty. Dust, crowding, and distance still shape every interpretation. The stars within Stephenson 2 also reveal differences among red supergiants themselves. Some are somewhat earlier in spectral type and less heavily altered by mass loss. Others are later in type, brighter in the infrared, and show stronger signs that their outer layers are becoming unstable and that material is being expelled into surrounding space. This range is important because it suggests the cluster contains red supergiants in slightly different stages of advanced evolution. The cluster is not simply a collection of identical red stars. It is a population that displays variation across a shared age and environment. In that variation, one star can stand out as more extreme than the rest. The physical setting of Stephenson 2 also hints at the recent history of the region. Massive stars do not live long, so a cluster dominated by red supergiants must represent an episode of vigorous star formation that occurred only a small fraction of the galaxy's lifetime ago. The cloud that formed these stars has largely changed or dispersed. What remains is the stellar population and the evidence of what the region was able to produce. Stephenson 2 is therefore both a present cluster and the surviving trace of a powerful earlier event of stellar birth in the inner Milky Way. At this layer of the story, the search has narrowed from the broader galaxy and the general logic of identification to one hidden stellar environment of unusual richness. The largest candidate star is no longer merely a possible red point among many. It belongs to a specific obscured cluster, within a specific crowded region of the galactic disk, among a rare concentration of evolved massive stars. The setting is now close enough that the individual object can begin to emerge, not yet through its own atmospheric edge or visible surface, but through the company, location, and dust-veiled cluster that hold it in place. Within the obscured population of Stephenson 2, one star stands out as more extreme than the others. This is Stephenson 218, often identified as the leading candidate for the largest known star by radius. Yet even here, at the point where attention narrows to the individual object, the star does not present a simple boundary. The next region inward is not a surface in the ordinary sense. It is the star's outer reach, the broad, fading envelope where glowing gas thins gradually into surrounding space. In a red supergiant of such scale, the edge is not a sharp line. It is a transition zone, and the meaning of size begins there. A star like Stephenson 218 is composed of hot gas held together by gravity and supported from within by energy generated in deeper layers. Its visible body is not solid. There is no crust, no shell, and no fixed outer wall. Instead, pressure and gravity shape a vast extended sphere of gas whose density decreases outward. Near the deeper interior, the gas is denser and more strongly bound. Farther out, it becomes thinner, cooler, and less tightly held. At some depth, light can escape freely enough to travel into space. This region forms the practical visible boundary used in stellar astronomy. It is not a hard edge, but it is the level from which the star's ordinary visible appearance mainly arises. For a red supergiant, that visible boundary lies astonishingly far from the centre. Observations and models for Stephenson. 218 suggest a radius measured in the thousands of solar radii, though the exact value remains uncertain because it depends on distance, luminosity, and temperature estimates. Even with this uncertainty, the implied scale is immense. If placed at the centre of the solar system, such a star would extend outward past the orbit of Mars and far into the outer planetary region, with some estimates reaching toward the orbit of Jupiter. This comparison is not a claim about a solid globe replacing empty space. It is a way of expressing how far the visible outer layers are spread from the centre when the star is interpreted through current measurements. That outer reach is diffuse. Gas in the envelope becomes steadily thinner with height, and the transition from star to surrounding medium is gradual rather than abrupt. In everyday objects, size is easier to define because a surface clearly separates object from surroundings. In a red supergiant, the visible edge depends on where the gas becomes transparent enough for most light to escape. Different wavelengths can trace somewhat different depths. Additional material above the formal photosphere, meaning the layer from which most visible light emerges, can still absorb, emit, or scatter radiation. This makes the boundary scientifically useful but physically extended. The enormous size of the outer envelope also means the pull of gravity at the visible surface is comparatively weak. The star is massive, but its outer layers are spread over such a huge volume that the gravitational hold on the uppermost gas becomes much less firm than it is at the surface of a smaller star. This weak surface gravity is one reason red supergiants have unstable and extended atmospheres. Gas near the outer reach is not held in a tight compact layer. It can be lifted, stirred, and slowly driven outward more easily. The star's great size is therefore not only a measure of scale, it is part of the physical reason why the outer layers behave in a loose and changing way. Light crossing this outer region does not emerge from a thin mathematical shell. It passes through depth. In a dense star, the interior is opaque, meaning light is absorbed and scattered many times before escaping. Near the outer envelope of a red supergiant, the gas becomes transparent enough that photons, the particles of light, can finally leave without repeated interruption. But this transition occurs through a range of depth, not at a single exact line. The visible stellar disk that astronomers infer is therefore a kind of luminous frontier, broad in physical meaning even when described by a single radius value. Because Stephenson 218 is so distant, its outer reach is not usually seen directly as an image with clear structure. It is inferred from the star's observed properties. Even so, the idea of this vast envelope is grounded in standard stellar physics. A cool and highly luminous star must possess an enormous emitting area. The outer reach is that area. It is the wide, cool, glowing skin of the star, though skin is only an analogy, because nothing there is firm or self-contained in the way an animal or planet has a skin. It is more accurate to think of a shining fog-like sphere, denser below, thinner above, bound together by gravity and sustained by deeper energy. At this distance from the centre, timescales also become different from familiar ones. The outermost layers are so expanded that motions through them can take long periods. Disturbances move across regions of enormous size. The light that leaves from one part of the visible surface does not come from a perfectly still background. It comes from gas that is part of a broad, slowly changing outer body. The star's appearance, if it could be viewed nearby, would not resemble a smooth ideal ball. It would be a giant luminous envelope with depth, motion, and uneven structure. The term radius can therefore hide as much as it reveals. It gives a single number that allows comparison among stars, and for that purpose it is essential. Yet in a star like Stephenson 218, radius refers to a chosen effective boundary within a gradual envelope. The star is not smaller than that number suggests, but neither is it neatly contained by a crisp surface. Its outer reach is an extended physical zone where light, gas, pressure, and gravity meet in a changing balance. The largest known star is largest not because it possesses a rigid circumference, but because its luminous outer layers have swollen outward to an extraordinary distance from the centre. At this stage, the object has become individual at last. It is no longer only a member of a hidden cluster or a candidate assembled from measurements. It is a real stellar body with a vast fading frontier. The story has entered the star itself, beginning from the furthest luminous reach, where size becomes visible not as a line, but as a great and diffuse expansion of glowing matter suspended against the dark of interstellar space. At the outer reach of a star like Stephenson 218, size alone does not explain what is seen. The next layer inward is the light of the visible outer body itself, where colour, temperature, and luminosity combine to reveal the nature of a red supergiant. A red supergiant appears red not because it is weak or fading in any ordinary sense, but because its visible surface is cooler than that of hotter stars. In stellar astronomy, colour follows temperature in a broad and useful way. Hotter stars tend toward blue or white light, while cooler stars tend toward orange or red. Red supergiants belong to the cool, luminous end of the stellar population, where the outer layers have expanded so greatly that the visible surface radiates at a lower temperature even while the total energy output remains enormous. This combination can seem counterintuitive at first. A star of extraordinary size might be expected to appear fiercely hot at its outer edge. Yet the opposite is often true. When a massive evolved star expands, the same broad requirement of energy balance applies across a much larger radiating area. The light is emitted from an immense visible surface, and because that area is so vast, the effective temperature of the outer layers can be lower while the total luminosity remains extremely high. Luminosity means the total amount of energy a star emits in all directions. Effective temperature means the temperature that describes the star's outgoing radiation in an idealized overall sense. Together, these quantities allow astronomers to understand why a red supergiant can look cool in color while still outshining the sun by a very large factor. In practice, the red color of such a star is not a single pure tone. The light from a red supergiant carries the imprint of molecules and atoms in a cool, extended atmosphere. The spectrum of these stars often shows features associated with lower temperatures, especially molecular absorption bands that become prominent in cool stellar photospheres. Those spectral patterns help astronomers estimate temperature and classify the star more securely than color alone can do. This is especially important in dust-rich regions of the Milky Way, because dust can also redden light. A genuinely cool supergiant and a hotter star seen through heavy dust may both appear red to a simple detector, but their spectra reveal very different physical conditions. The star's true color therefore emerges not from appearance alone, but from the detailed behavior of its light. For an extreme object such as Stephenson 218, the estimated effective temperature is low by the standards of massive stars, in the range expected for a red supergiant rather than for a hot blue supergiant or an O-type star. Even so, low in this context still means thousands of degrees. The visible layers of a red supergiant are cool only by stellar comparison. They remain intensely hot in any ordinary physical sense. This distinction matters because the word cool can otherwise mislead. A red supergiant is not dim embers in space. It is an immense luminous sphere whose outer light emerges from gas hot enough to shine strongly, yet cool enough relative to other stars to shift much of the visible impression toward red and to allow molecules to survive in the upper photosphere. The relation between color and luminosity is one of the reasons these stars are so striking in stellar evolution. A compact hot star can be very luminous because each unit of its surface radiates intensely. A red supergiant reaches great luminosity in a different way. Its outer layers are spread over a tremendous area, and the huge radiating surface compensates for the lower temperature at each part of that surface. This is why the largest known stars are also among the most luminous cool stars. Their light does not come from heat concentrated in a small place. It comes from moderate stellar heat extended across a huge visible body. The star's red glow is therefore inseparable from its size. The very expansion that makes it vast is also what lowers the apparent temperature of its visible outer layers. This outer glow is not perfectly uniform. Observations of nearer red supergiants such as Betelgeuse and Antares show that their visible surfaces and upper atmospheres can be irregular, with large-scale structure changing brightness patterns, and extended material above the photosphere. These nearby examples do not serve as exact copies of Stephenson 218, but they provide a physically grounded model for how cool supergiant light emerges from a dynamic outer body rather than a smooth fixed shell. When astronomers interpret the colour and brightness of a distant extreme red supergiant, they do so with the understanding that its outer layers are likely structured, variable, and extended, not simple and static. The infrared is especially important here. A cool luminous star emits strongly at longer wavelengths, and dust along the line of sight is less destructive in the infrared than in visible light. This makes infrared observation one of the main ways to recover the true output of distant red supergiants hidden in the inner Milky Way. In heavily obscured environments like the Stephenson 2 region, the visible impression of the star can be deeply altered before it reaches Earth, but the infrared carries more of the star's own energy through the dust. The measured luminosity of such a star therefore depends strongly on combining observations across wavelengths and correcting carefully for extinction, the dimming and reddening caused by intervening matter. Without that work, the star's true scale would remain hidden behind the galaxy itself. Because of these corrections and model choices, the exact luminosity and temperature assigned to Stephenson 218 remain uncertain. That uncertainty matters, because radius is derived from those values. A small change in effective temperature can produce a large change in inferred size for such a cool and luminous object. This is one reason astronomers often describe Stephenson 218 as a leading candidate for the largest known star rather than as an unquestioned final record holder. Observations indicate an extreme red supergiant of immense radius, but the precise number depends on how the light is interpreted through dust, distance, and atmospheric modelling. The scientific picture is therefore strong in its general conclusion and cautious in its exact detail. At this layer, the star is understood through the character of its glow. Its colour reveals a cool outer body by stellar standards. Its luminosity reveals the enormous total energy released across a vast surface. Its spectrum reveals a low-density extended atmosphere, and its infrared strength reveals how much of its true nature would be lost without looking beyond visible light. The largest known star becomes comprehensible here not as a number alone, but as a red luminous presence whose great size is written directly into the soft, cool light escaping from its outermost visible layers. Beyond the visible photosphere of a red supergiant lies a still broader region of gas, motion, and gradual escape. This is the extended atmosphere and wind, where the star no longer holds all of its outer matter securely. In a star such as Stephenson 218, the visible surface is only part of the story. Above it, the atmosphere continues outward through cooler and thinner layers, and within those layers the star begins to lose mass to surrounding space. The next region inward is therefore not a quieter layer beneath the surface, but the outer atmospheric domain itself, where gas rises, cools, forms dust, and drifts away. This is one of the defining traits of a red supergiant. It is not only immense, it is slowly shedding part of its own body into the galaxy. The atmosphere of a red supergiant is far more extended than that of a compact star. Because the visible surface gravity is weak, gas above the photosphere is not held tightly in place. Motions from below can lift it. Pulsations, meaning large-scale rhythmic expansions and contractions, can push material outward. Convection, the transfer of heat by rising and sinking gas, can send vast currents upward through the outer layers. Radiation pressure on dust can also help drive matter away once solid grains begin to form in cooler regions above the visible surface. None of these processes acts alone in a simple and final way. The atmosphere is shaped by their combination, and the result is a broad, unstable envelope in which matter is constantly being rearranged. In a star of this kind, the atmosphere is not a smooth shell. It is clumpy, irregular, and changing. Gas rises in some regions and falls in others. Cooler pockets can form where molecules survive and where dust begins to condense from material that has expanded far enough from the hotter layers below. Dust here means tiny solid particles made from heavier elements created in earlier generations of stars and now present in the gas of the red supergiant itself. Once formed, these grains interact strongly with starlight. Light carries momentum, and when photons strike or are absorbed by dust, they can push the dust outward because gas and dust remain coupled through collisions and shared motion. This outward push can help carry surrounding gas into the stellar wind. Mass loss is the name given to this steady outward escape of material. For a red supergiant, it can be substantial on stellar timescales. The star does not vanish quickly, and the outflow is not a violent explosion in its ordinary late stage, but year after year matter leaves the atmosphere and enters circumstellar space, meaning the region around the star itself. Over long periods, this loss can remove a meaningful fraction of the star's outer envelope. The red supergiant stage is therefore not only a swollen state, it is also an erosive state, in which the star continually parts with the gas that once belonged to its outer body. This outflow is important for two reasons. First, it changes the future of the star. The amount of mass retained or lost affects how later stages of evolution unfold. Second, it enriches the surrounding medium. Gas and dust expelled by red supergiants become part of the interstellar material from which later stars and planets may eventually form. The star's wind is therefore both personal and galactic. It is a local atmospheric escape and a contribution to the larger cycle of matter in the Milky Way. The wind itself is slow compared with the winds of hotter, massive stars. In hot blue stars, strong radiation acting on ions can drive faster and more forceful outflows. In red supergiants, the wind tends to be denser and slower, carried by the combined effects of pulsation, atmospheric lifting, molecule and dust formation, and radiation pressure on that dust. The gas moves outward at speeds that are large on human terms but modest by stellar standards. This gentler pace gives the outflow a different character. It creates an extended dusty environment rather than a sharply driven high-speed stream. Around some red supergiants, observations reveal shells, arcs, or irregular clouds of ejected matter. Nearby examples show that mass loss does not occur as a perfect steady breeze. It can vary with time and direction. Large convective events on the surface may launch more material from one area than another. Pulsation may strengthen or weaken for periods. Dust production may become more efficient in some intervals. The result is a circumstellar environment marked by asymmetry and memory, where the gas around the star preserves traces of earlier episodes of outflow. Although Stephenson 218 is too distant to map in the intimate detail possible for nearer red supergiants, it belongs to the same broad physical category, and its great size and advanced state strongly suggest an extended mass-losing atmosphere. This atmospheric outflow also affects the light by which the star is judged. Dust formed in the circumstellar region can absorb and re-radiate energy, especially in the infrared. A star surrounded by its own expelled material may therefore appear different depending on wavelength. Some of the visible light is dimmed. Some of the absorbed energy reappears at longer wavelengths. This is one reason why infrared observations are so important in understanding large red supergiants. They help trace not only the star's own cool luminous body, but also the dusty matter the star has recently released. The atmosphere and wind are therefore part of the difficulty in measuring the star. The edge is not fixed. The escaping material can alter observed brightness and colour. The outer layers are extended, mobile, and not in perfect equilibrium. A simple model of a quiet sphere is useful for first estimates, but the real object is more complicated. It is a star in the act of loosening its outer hold on matter. In this region, the largest known star appears less like a stable object and more like a vast source of gradual release. Its atmosphere stretches outward beyond the visible boundary. Its gas rises and cools. Dust takes shape in the lifted material. Light pushes part of that material away. Over time, the star breathes matter into space, though not in any literal biological sense. It is better understood as a giant gravitational body whose weakened outer grip allows the outermost envelope to drift outward under the influence of motion, cooling, and radiation. At this stage of the inward path, the star is no longer defined only by its red light and enormous radius. It is defined by what leaves it. The outer atmosphere is an active threshold between bound stellar matter and matter returning to the galaxy. The larger stars are not only large reservoirs of gas, they are also places where the boundary between star and space grows porous, and where the star begins to give part of itself back to the wider Milky Way. Below the extended wind and the drifting circumstellar matter lies the visible surface region of the red supergiant itself, though surface in this case remains only a convenient word. In a star such as Stephenson 218, the visible outer body is not fixed like the skin of a planet. It is a broad luminous layer shaped by moving gas, changing brightness, and slow but persistent instability. The next region inward is therefore the photospheric domain, where the star's light emerges through motion rather than stillness. Here the great radius is expressed not only in scale, but also in the behaviour of matter spread across an immense and weakly bound outer body. The visible surface of a red supergiant is governed by convection. Convection is the transfer of heat by rising and sinking material. In the Sun, convection produces granulation, a pattern of many small bright cells and darker boundaries. In a red supergiant, the same process operates under very different conditions. The star is vastly larger. The surface gravity is far weaker, and the outer layers are cooler and more extended. As a result, the convective pattern is not made of countless small cells. Observations and models indicate that only a small number of very large convective regions may dominate the visible surface at one time. Each of these regions can cover an enormous fraction of the stellar disk. Within such a cell, hotter gas rises from deeper layers, expands, cools, and eventually sinks again elsewhere. The temperature differences are not extreme in absolute terms, yet they are enough to alter the brightness of the visible surface. A region where hotter material rises appears brighter, a cooler region appears dimmer. Because the cells are so large, the star's visible face is likely uneven rather than smoothly radiant. If an observer could see Stephenson 218 from nearby with sufficient protection and resolution, the star would probably not appear as a uniform red sphere. It would more likely appear mottled, with broad luminous patches and darker regions shaped by giant convection. These surface structures do not stand still. Gas moves through them on timescales of months to years, depending on the depth and scale involved. The visible face changes as the convective pattern evolves. Some cells strengthen, some fade, and some are replaced by others. This helps explain why red supergiants are often variable stars. Their brightness changes because the outer layers are dynamic. The variation is not usually the result of one simple clock alone. It reflects the combined influence of convection, pulsation, changing atmospheric conditions, and sometimes the formation of dust above the surface. Pulsation adds a further layer of motion. A pulsating star undergoes repeated expansion and contraction in part or in whole. In a red supergiant, these motions can be irregular or semi-regular rather than perfectly periodic. The star's outer layers respond to deep pressure changes and to the difficulty of maintaining full equilibrium in so vast an envelope. The visible radius may shift somewhat over time. The brightness may rise and fall. The speed of gas moving upward or downward through the atmosphere can change. Pulsation is therefore not separate from the surface. It is one of the ways the surface reveals that the star is not fully settled. The weak surface gravity of a red supergiant is central to all of this. The star remains massive, but its outer layers lie so far from the center that gravity at the visible surface is relatively feeble. In that condition, convection can drive large-scale motions more easily. Pulsation can lift material farther, turbulent pressure, meaning the effective support produced by chaotic gas motion becomes more important. The visible surface is therefore a place where gravity still rules in the broad sense, yet where local motions and instabilities can strongly shape what the star looks like from outside. This behavior has been observed most directly in nearer red supergiants such as Betelgeuse and Antares. High-resolution studies of those stars reveal asymmetries, changing bright regions, and atmospheric motions that confirm the general picture of a giant unstable photosphere. Stephenson 218 is much farther away, so its surface cannot be mapped in the same direct detail with present methods. Even so, the physics of red supergiants gives strong reason to expect similar behavior there, and perhaps on an even grander scale because of the star's extreme size. The surface of such a star is not calm simply because it appears as a point of light from Earth. Its stillness is only apparent at distance. Instability at the surface also helps connect the photosphere to the atmosphere and wind above it. A strong upward convective event can lift gas into cooler layers where molecules and dust can form. A pulsational cycle can help push outer material to greater height. These motions do not by themselves guarantee mass loss, but they prepare the conditions under which the atmosphere becomes easier to disturb and easier to drive outward. The visible surface is therefore the engine room of much of the behavior described in the outer atmosphere. What drifts away in the wind often begins as motion here, at this level. The meaning of radius grows more subtle once again. A published value for the radius of Stephenson 218 suggests a single size, but the visible surface is active and changing. The star is not breathing in a literal biological sense, yet its outer body does expand, shift, brighten, dim, and reorganize over time. The radius used in astronomy is a useful average description of the layer from which most light escapes. It does not imply a rigid shell frozen in place. The largest known stars are large in a living physical sense, not because they are alive, but because their outer matter is constantly in motion. This restless surface also helps explain why measurement remains uncertain. A temperature estimate based on one phase of variability may not match the exact state of the star at another time. Brightness changes can affect derived luminosity. Extended material above the photosphere can alter the observed spectrum. The star's enormous size is real in the sense that every plausible interpretation still places it among the most expanded known stars. But the exact number assigned to that size reflects an object whose visible surface is never perfectly still. In this region, The largest known star becomes a place of motion spread across a vast scale. Convection lifts great fields of hot gas. Cooler regions descend. Pulsation gently swells and relaxes the outer body. Brightness changes pass across the photosphere over long intervals. The visible face is not a smooth lantern, but a restless luminous terrain made of gas held only loosely at the edge of a star near the late stages of its life. The story has moved inward to the place where the star's light is born into space, and that place is dynamic, uneven, and always in the process of changing. The visible surface of a red supergiant is broad, bright, and changing. Yet the title of a largest known star does not come from direct inspection of that surface alone. It comes from measurement, and measurement in this case is an act of inference. The next region inward is therefore not a physical layer of gas, but the method by which the star's size is determined from light. For a distant object such as Stephenson 218, radius is not usually measured by drawing a clear edge around a resolved disk in the sky. It is derived from the relation between luminosity and temperature, and because both of those depend on uncertain quantities. The final size remains impressive yet not perfectly fixed. The first required quantity is luminosity, the total energy the star emits into space in all directions. This is not the same as apparent brightness, which is only the amount of light arriving at Earth, to move from one to the other. Astronomers must know the distance. A nearby faint star can look brighter than a distant luminous one. The farther away the star, the more its light spreads before it reaches an observer. If the distance is underestimated, the luminosity will also be underestimated. If the distance is placed too far, the luminosity will become too large. Because radius depends strongly on luminosity, every uncertainty in distance enters the final estimate of size. Distance is especially difficult for extreme red supergiants in the inner Milky Way. The line of sight crosses dense and dusty parts of the galactic disk, where many stars at different depths can overlap in the same apparent field. The star may seem associated with a certain cluster, and that association may well be correct. But the cluster distance itself can carry a meaningful range of possible values. Some measurements rely on the broader stellar population. Some rely on galactic structure models. Some depend on more direct but still imperfect methods. Each carries its own limitations. As a result, a star can be securely recognized as very large without its exact radius being known to the last detail. The second required quantity is effective temperature. This is estimated from the spectrum and from the general behavior of the star's light across wavelengths. In a cool red supergiant, temperature is not measured by touching a surface or by reading a fixed value from a sharply defined photosphere. It is inferred from models of how such a star radiates, and those models must account for molecular absorption, extended atmospheric layers, variability, and dust. A change of only a modest amount in the adopted effective temperature can shift the inferred radius significantly. This is because a cooler star must have a larger area to emit the same luminosity. For very expanded cool stars, the radius becomes especially sensitive to the temperature scale used. Dust introduces another major source of uncertainty. Intervening dust in the Milky Way dims and reddens the star before its light reaches Earth. Dust close to the star can do the same. To recover the intrinsic luminosity, astronomers correct for this extinction, meaning the loss and alteration of light by intervening matter. Yet extinction is not always simple to model. Dust grains differ in size and composition. The distribution of dust may be patchy. A star surrounded by its own outflowing dusty material may not follow the same correction pattern as a clearer object. Small differences in how extinction is treated can change the recovered luminosity enough to affect the radius estimate. The spectrum, too, can be interpreted in more than one reasonable way. Red supergiants are not ideal static spheres. Their atmospheres are extended and dynamic. Their visible surfaces show large convective structure. Their upper layers may contain molecules and dust that alter the outgoing light. Because of this, the relation between observed spectral type and effective temperature is not perfectly settled for the most extreme cases. Two careful studies can examine similar data and still arrive at somewhat different temperatures, luminosities, and therefore radii. This does not mean the measurements are unreliable in a general sense. It means the object itself resists oversimplification. For this reason, the phrase largest known star is best understood as a leading measured interpretation rather than an eternal final title. Stephenson, 218 is widely treated as one of the strongest candidates, and often the strongest candidate, for the largest radius among known stars. Observations indicate an extraordinary red supergiant whose inferred radius lies far above that of ordinary stars and above most other supergiant candidates. Yet it remains uncertain whether the exact value is the highest possible among all currently known objects under every model and every future revision. The scientific conclusion is therefore firm in rank and careful in wording. The star belongs at the extreme upper end of known stellar size, while the precise record remains tied to the quality of measurement. There is also the question of what is being measured when radius is given. The radius of a red supergiant refers to a practical photospheric boundary, not a hard solid surface. Different wavelengths can probe slightly different depths in the atmosphere. Extended material above the photosphere can contribute to or modify the emerging light. In some studies, the effective radius relevant to one observational method may not align perfectly with the radius inferred through another. Again, the star remains vast in any case, but the act of assigning one single number compresses a layered and changing reality into a simplified result. Nearby giant stars can sometimes be measured more directly through interferometry, a method that combines light from separated telescopes to achieve very high angular resolution. Such techniques have been used to estimate the sizes of stars like Betelgeuse and Antares. For much more distant stars such as Stephenson 218, the challenge grows enormously. The star is too far away for its disk to be measured with the same clarity through ordinary direct means. This is why indirect inference remains central. The largest stars are often known through the disciplined interpretation of light rather than through direct imaging of a neatly resolved sphere. Variability makes the task still more delicate. A red supergiant changes over time. Brightness, spectral appearance, and atmospheric structure can shift from one observing period to another. A study based on one set of observations may capture the star in a somewhat different state from another study. If the star is brighter, cooler, or more dust-obscured at one time than at another, the inferred radius will move accordingly. The star does not stop being immense, but the exact number attached to its size remains part of an evolving picture. In this region of the story, the largest known star is measured rather than seen outright. Its size is assembled from distance, corrected brightness, spectral interpretation, and thermal modelling. Each element is grounded in observation, and each carries uncertainty. What emerges is not confusion, but disciplined caution. Stephenson 218 stands as an extraordinary example of stellar expansion, likely among the very largest stars yet identified, and quite possibly the largest known by current estimates. But the science remains careful, because stars of this kind are not simple objects, and light from them travels through many layers of uncertainty before it becomes a number on a page. Beneath the unstable visible surface and the slowly changing outer envelope lies the deeper structure that allows such a star to remain expanded at all. The next region inward is the internal layering of the red supergiant, where energy from nuclear burning and the flow of heat through matter support the enormous outer body. This part of the star cannot be seen directly. It is understood through the physics of stellar evolution, through comparison with other massive stars, and through models that match the observed light and late evolutionary state of red supergiants. In this hidden region, the star is no longer defined by color or atmospheric drift. It is defined by the arrangement of burning shells and the balance between gravity and outward pressure. A massive star does not spend its whole life in the form of a red supergiant. Earlier in its life, it is more compact and hotter at the surface while it steadily fuses hydrogen into helium in its core. That long, stable period ends when the hydrogen in the center becomes exhausted. The core then changes. Without hydrogen fusion at the center to provide the same outward support, the core contracts under gravity. As it contracts, it grows hotter. This higher temperature allows new forms of fusion to begin in deeper layers and in shells around the core. The star responds as a whole. The outer layers expand to great distances, the surface cools, and the star enters the red supergiant stage. Inside this evolved structure, burning no longer occurs in just one simple central region. Instead, the star becomes layered. A shell of hydrogen fusion may continue outside the core, while deeper regions engage in helium burning, and later more advanced fusion stages. A shell, in stellar terms, means a roughly spherical layer where temperature and pressure are sufficient for a particular kind of nuclear fusion to proceed. These shells do not form as perfectly neat and motionless bands, but the layered picture is a useful description of the general structure. Each shell contributes energy. Each is part of the chain that supports the swollen outer envelope against the pull of gravity. Helium burning in the interior produces heavier elements, especially carbon and oxygen. In a sufficiently massive star, the process continues beyond helium after later contraction raises the central temperature again. The deeper interior then becomes more complex over time, with additional burning stages possible in successively inner regions. The red supergiant therefore contains a history of stellar change written inward. The outer body remains broad and cool, but the inner star is becoming denser, hotter, and more chemically layered. It is still one star, yet different depths within it belong to very different physical conditions. This layered burning is what makes the enormous radius possible. The outer envelope of a red supergiant is not expanded by emptiness alone. It is held up by pressure generated by the transport of energy outward from the burning interior. Some of that energy moves by radiation, meaning light and other electromagnetic energy passing through matter. In other regions, especially the cool extended envelope, convection becomes dominant, carrying energy outward through the rising and sinking of gas. The combination of these transport processes allows the star to establish a swollen structure, rather than collapsing into a much smaller body. The outer layers are loose and extended because the internal state of the star has changed in a fundamental way. The envelope itself contains much of the visible size of the star, but only a limited share of the star's deeper density. In a red supergiant, matter is not distributed evenly from center to surface. The inner regions contain far more of the gravitational concentration. The outer envelope occupies an immense volume but at low average density. This is why the star can be so large without having a mean density, anything like that of a planet or a compact star. In fact, The average density of the full star is extremely low when spread over such a huge sphere, yet this should not give the impression of insignificance. The outer envelope is still part of a powerful gravitational system sustained by energy from far below. Convection in the envelope links the interior to the visible surface. Heat rising from deeper layers drives the giant convective cells inferred for red supergiants. The broad surface variability described earlier is therefore a visible expression of inward structure. What happens in the deep envelope is not separate from what is seen at the photosphere. The star's great visible motions are consequences of how energy travels outward through a vast, cool outer body. In this sense, the visible star is the outer language of the hidden layers beneath it. The internal structure of a red supergiant is also sensitive to mass loss. As the star sheds its outer material through wind and atmospheric escape, the total mass decreases. That can affect the pressure profile, the later burning history, and the exact path the star follows through advanced evolution. Two stars with similar initial mass may not evolve in exactly the same way if one loses more mass than the other. This is one reason why theoretical models of the largest red supergiant still contain uncertainty. The basic picture of layered burning is secure, but the details of timing, envelope structure, mixing, and later transformation depend on factors that are difficult to measure directly. Mixing itself is important. Convection and other internal motions can bring processed material from deeper layers toward the surface, altering the chemical signatures seen in the atmosphere. This helps explain why evolved massive stars often show surface evidence of internal nuclear processing. The star is not fully sealed layer by layer. Matter and energy move. The deep interior and the visible exterior remain connected through transport and mixing, even though their physical conditions are very different. At this stage of the inward path, the star is no longer merely a vast red light in space. It has become a layered furnace. Hydrogen burns in outer shells. Helium burns deeper within. The core contracts and heats as each major fuel source is exhausted. The envelope expands because the interior has entered a more advanced and less stable mode of existence. The largest known star is therefore large not by accident, but because it is in a particular late state of stellar evolution where deep structural change has transformed the entire body. In this hidden interior region, the immense outer radius gains its true cause. The red supergiant is expanded because its life has moved beyond the simplicity of central hydrogen burning and into the stratified condition of a massive evolved star. Its outer layers shine softly and drift toward space, but below them the star is ordered into shells of fusion and support, all surrounding a core that's becoming progressively hotter, denser, and more decisive in shaping what the star will become. Deeper than the burning shells and the vast convective envelope lies the contracting core, the most inward region yet reached in the life of the red supergiant. Here the star becomes denser, hotter, and more compressed with each major step of evolution. The outer layers remain enormous and comparatively cool, but the core follows a different path. It grows smaller as gravity draws matter inward, and in doing so, it grows hotter. This inward contraction is not a failure of the star. It is the mechanism by which the star reaches each new stage of nuclear burning. The next region inward is therefore the deep core, where heavier elements are formed in sequence and where time itself begins to shorten. When hydrogen burning ends in the center, the core contracts until helium burning can begin. Later, when helium is exhausted in the center, the same pattern continues. The core contracts again. The temperature rises further, and new burning stages become possible if the star is massive enough. Carbon can ignite, then later neon, oxygen, and silicon in successively deeper and hotter phases. Each stage requires higher temperature and pressure than the last. Each stage also lasts for less time than the one before it. The general pattern is secure in stellar theory. A massive evolved star advances through increasingly rapid central burning phases until it can no longer gain energy by fusion in the same way. The reason these later stages become shorter is rooted in the physics of nuclear burning and gravity. Earlier fuels are more abundant and can support the star for far longer intervals. Later fuels are used under more extreme conditions and produce support for much shorter spans. The core is fighting gravity with each new fuel, but the contest becomes harder as the available reactions change. In very massive stars, the late sequence can accelerate dramatically. The long era of hydrogen burning may last millions of years. Helium burning is shorter. The later advanced stages become progressively briefer, until the final steps occupy only a very small fraction of the star's total life. This means that the deepest core is not only a place of heat and density, it is also a place where the star's remaining lifetime is compressed into a rapidly changing structure. The red supergiant still appears broad and calm from a great distance. Its light is soft, its atmosphere drifts outward, yet deep inside, the core has entered a much more urgent physical state. A quiet outer appearance can therefore conceal an interior that is evolving on increasingly short timescales. As heavier burning proceeds, the core becomes chemically layered in an inward sense as well as outward. The result is often described as an onion-like structure, with different burning shells wrapped around a central core made of heavier and heavier elements. This image is useful if treated carefully. It does not mean the layers are perfectly smooth or permanently fixed. Convection, mixing, and changing burning conditions can complicate the picture. Even so, the general idea remains sound. Hydrogen burns in an outer shell. Helium burns deeper in. Still deeper regions may host carbon, neon, oxygen, or silicon burning, while the center becomes increasingly dominated by the ash of previous stages. The ultimate product of this inward progression is an iron-rich core. Iron is decisive because fusing iron into heavier elements does not release energy in the same way that earlier fusion stages do. Up to iron, fusion can provide support by releasing energy. Beyond that point, the balance changes. Once the core becomes dominated by iron group material, the star approaches a limit. It can no longer rely on further ordinary fusion in the center to hold gravity back. The core is then supported only temporarily by pressure in dense matter, and that support has limits. Before that final point is reached, the deep core is already a region of extreme compression. Electrons, the light negatively charged particles in atoms, become increasingly important in determining pressure under such conditions. Matter is no longer behaving in the familiar low-density way of gases near a stellar surface. The atomic structure that matters in cooler outer layers becomes far less relevant here. The core is dense, hot plasma under immense gravitational stress. The physical language of ordinary substances no longer applies well. It is better understood as matter in an advanced stellar state, with nuclei, electrons, radiation, and pressure all interacting under conditions far removed from everyday experience. Neutrinos also become important in these deep stages. Neutrinos are extremely light particles that interact only weakly with matter. In the advanced interiors of massive stars, some processes produce neutrinos in large numbers, and because these particles escape so easily, they can carry energy away from the core. This cooling effect matters. It allows contraction to continue and helps shape the timing of the late burning phases. The deeper the core evolves, the more this invisible loss of energy influences the path toward collapse. The core of an extreme red supergiant is therefore very different from its visible body. The outer star is huge and low in average density. The inner core is compact and increasingly dense. The outer star changes on timescales that can be observed through variability and mass loss. The inner core can pass through decisive transformations much more quickly near the end. The two regions remain connected, but they belong to different physical regimes. The largest known star contains, at its center, not a broad echo of its outer immensity, but a deep contracting heart where gravity steadily gathers power. This inward concentration also explains why a star can be both vast and fragile. Its outer radius may be greater than that of almost any other known star, yet its future depends on processes occurring in a core that is small by comparison. The fate of the enormous envelope rests on what happens in this compact region. Once the core reaches the point where it can no longer support itself through ordinary fusion, the rest of the star cannot remain as it is. The outer immensity depends completely on the inner balance, and that balance is becoming harder to maintain. At this depth, the largest known star is no longer best understood as a red giant lantern in space. It is a star nearing the end of what thermal fusion can sustain in its center. The deep core contracts, heats, changes fuel, and grows heavier in composition. Each stage grows shorter. Each inward step leaves less room for stability. The immense outer star still shines above, but below that shining body the core is moving toward a limit set by the physics of matter, gravity, and nuclear energy. The path inward has reached the place where stellar greatness narrows into compression, and where the largest stars begin to approach the boundary of how long such expansion can continue. Beyond the contracting core and the sequence of heavier burning stages, the star enters its final evolutionary state as a red supergiant. This state is not defined by a single instant, but by a narrowing range of possibilities in which the outer star remains extended while the inner support grows less secure. The next region inward is therefore the late condition of the whole star as an ending physical system. At this stage, the red supergiant is still present as a vast luminous body, but its structure is under increasing strain from within. The outer envelope, the burning shells, the mass loss, and the core all remain connected, and the star's future depends on how long that connection can hold. In the late red supergiant state, mass loss becomes one of the central processes. The star has already spent time shedding material from its extended atmosphere, but as evolution advances, this loss can become increasingly important in shaping what remains. The envelope is not just a passive outer layer. It is the great reservoir that gives the star its swollen red form. As matter escapes, the total mass of the star declines, and the balance between gravity and pressure shifts again. The star may still remain enormous, but the structure supporting that enormity becomes more delicate. A red supergiant near the end is therefore not simply a large star waiting unchanged. It is a star being gradually reduced by its own wind while its deep interior continues to transform. Observations of red supergiants indicate that this late condition is not perfectly smooth or steady. Some show stronger variability, more substantial dust production, or signs of enhanced instability in their outer layers. In some cases, the circumstellar environment becomes richer in expelled material, suggesting that the star has undergone episodes of more active loss. The physical causes can include pulsation, surface convection, changes in atmospheric structure, and the deep evolutionary state of the interior. The outer body may therefore become increasingly irregular as the star approaches the end of its red supergiant phase. What is seen from afar as a red luminous point may in reality be a changing system surrounded by its own recently shed matter. This late state is also shaped by uncertainty. Observations indicate that many massive stars pass through a red supergiant phase, but it remains uncertain whether every star of a given initial mass stays in that state until core collapse. Some may lose enough mass to move back toward hotter temperatures before the final collapse. Some may pass through additional unstable stages. The exact path depends on the initial mass, chemical composition, rotation, internal mixing, and mass loss history. For the most extreme red supergiants, this means the broad picture is known while the final route remains partly unsettled. The star is clearly near the end of massive stellar evolution, yet the precise track through the last stages can differ from one object to another. Stevenson. 218 belongs within this uncertainty. Its inferred size and advanced red supergiant nature place it among the most evolved swollen stars known, but observations alone do not allow every detail of its remaining life to be specified. It is known as a cool, luminous, mass-losing giant in a late phase. It remains uncertain exactly how much mass it has already lost compared with its birth mass, how long it can remain in its present extended condition, and whether it will end its life directly from the red supergiant stage or after some additional transformation. These are normal uncertainties in the study of distant evolved massive stars, not signs that the general understanding is weak. The star is clearly in a terminal part of stellar evolution. The question is not whether it is near the end, but how that end is physically reached. As the core approaches its final limit, the burning shells above it also become more compressed into shorter and less stable intervals. The outer star still depends on energy from below, but the deep interior is no longer able to provide long-lasting stability. The core becomes more dominated by iron group material. Neutrino losses grow important. Pressure support becomes increasingly difficult to maintain in the deepest region, yet none of this is visible directly at the surface in a simple and immediate way. The red supergiant can continue to shine with a calm appearance even while the inner star enters its most advanced state. The late evolutionary condition is therefore one of contrast. The outer star remains slow and expansive. The inner core approaches a rapid and decisive threshold. This threshold is the limit of core support. Once the central core exceeds what can be held up by the relevant pressure in dense matter, collapse begins. The exact sequence beyond that point depends on conditions within the core and envelope, and it remains an area of active study how different massive stars produce different final events. In broad consensus, however, the red supergiant stage leads toward core collapse rather than quiet fading. The star does not simply cool into darkness while keeping its immense form. Its deep structure makes that impossible. Gravity ultimately wins in the core once fusion can no longer provide sufficient resistance. Even so, there is caution in how the final outcome is described. Some red supergiants are expected to end as hydrogen-rich core collapse supernovae, particularly of the general kind associated with extended cool progenitors. Yet not all details are settled for the most massive and heavily evolved stars. Observations indicate that mass-lost envelope structure and pre-collapse instability can alter what the final event looks like and how much of the outer star is still present when collapse begins. In some stars, the envelope may remain broad and substantial. In others, much of it may already have been reduced. The late red supergiant state is therefore best understood as an approach to collapse shaped by a contest between internal evolution and outward mass loss. This end state also has a larger meaning within the galaxy. The The matter expelled in the final red supergiant phase enriches the local interstellar environment before the star's last transformation occurs. The star contributes gas and dust even before its terminal event. By the time collapse arrives, it is not a closed system. It has already begun transferring part of its substance back into surrounding space. The final stage of the largest stars is therefore not only an ending, it is part of the ongoing circulation of matter in the Milky Way. At this inward depth, the largest known star is seen as a whole system nearing its final structural limit. Its outer envelope is still vast and red. Its atmosphere still loses matter. Its surface still moves through broad convection and variability. But the hidden support beneath these features is weakening as the core approaches the point where further ordinary fusion can no longer preserve equilibrium. The final evolutionary state of a red supergiant is not a dramatic pose, it is a narrowing of stability. The star remains immense, but the conditions that make such immensity possible are steadily being exhausted. What endures for a time as one of the largest known stars is, in this late condition, also one of the clearest examples of how even the greatest stellar expansion must eventually yield to gravity. At the deepest level of this subject, beyond the late state of one red supergiant, the meaning of the largest known star becomes clearer. The final region inward is not a smaller physical layer inside the star, but the scientific meaning carried by such an object within the life of the universe. A star like Stephenson 218 is important not merely because it holds a possible record. It matters because it reveals how far stellar structure can be stretched while still remaining a star, how gravity and pressure can briefly sustain an enormous envelope, and how the lives of massive stars connect to the larger history of matter in the galaxy. In this inward sense, the greatest known stars are not curiosities alone. They are limits made visible. A star becomes meaningful in astronomy when it helps define a boundary. The largest known stars mark a boundary in radius, but that boundary is tied to other limits as well. There is a limit to how large a star can grow while still keeping its outer layers bound. There is a limit to how cool and extended a luminous massive star can become before instability and mass loss begin to reshape it. There is a limit to how long such a state can last before the deep core reaches a new stage and forces the whole structure onward. A red supergiant at the edge of known size therefore shows not a permanent form, but a temporary maximum in the range of stellar possibility. This is why the study of such stars belongs to stellar evolution rather than to simple classification. A classification says what a star is. Evolution explains how it came to be that way and why it cannot remain so forever. The largest red supergiants reveal that stellar life is not a straight path from birth to death. It is a changing sequence in which internal nuclear burning, outward energy transport, atmospheric escape, and gravity continually reshape the body of the star. The larger stars are especially valuable because they amplify these processes. Their huge envelopes make convection and mass loss easier to study in principle. Their extreme luminosities illuminate the connection between internal burning and outer expansion. Their rarity reminds astronomy that the most striking states of matter in the universe are often short-lived. They also reveal the importance of uncertainty in scientific knowledge. Stephenson 218 is widely treated as a leading candidate for the largest known star, and perhaps the largest known by current estimates, yet the exact record remains linked to measurement, distance, extinction, temperature scale, variability, and atmospheric modelling all influence the derived radius. This does not weaken the meaning of the star. It strengthens the discipline by showing that astronomy does not depend on spectacle alone. It depends on careful interpretation, on limits honestly stated, and on the distinction between what observations strongly support and what remains unsettled. In this way, the largest known stars teach not only about physics, but also about scientific method. Their role in the galaxy is just as important. Massive stars live quickly and die young. During their lives, they shape surrounding space through radiation, winds, and later the release of enriched matter. In the red supergiant stage, they return gas and dust to the interstellar medium. In their terminal collapse, they may contribute further heavy elements and kinetic energy to the galaxy. The chemical richness of later stars, planets, and eventually the material basis of rocky worlds depends in part on generations of massive stars that lived and ended before them. The largest stars are therefore not separate from cosmic history. They are participants in the long circulation of matter through stellar birth, evolution, death, and renewed formation. A red supergiant also clarifies scale in a way few objects can. The Sun defines ordinary stellar experience for life on Earth, but it does not define the full range of what a star can become. A star thousands of times wider than the Sun shows that the category star contains an immense diversity of physical states. One kind of star can remain stable for billions of years in moderate form. Another can swell to extraordinary size, lose matter through a diffuse wind, and approach collapse after only millions of years. The universe does not produce stars according to one quiet pattern. It produces them according to the possibilities allowed by mass, composition, pressure, gravity, and time. The largest known stars also draw attention to the contrast between appearance and reality. From Earth, such a star is little more than a point, dimmed by distance and dust. Its immensity is hidden inside ordinary starlight. This contrast is part of the quiet force of astronomy. The greatest structures are often inferred from small signals. A faint red point in the inner Milky Way, carefully measured, becomes an object larger than the orbit of inner planets, and perhaps extending toward the realm of outer ones if imagined in the solar system. A hidden cluster behind dust becomes the birthplace of some of the most expanded stars known. The universe often conceals its scale until light is read correctly. There is also a philosophical restraint built into the science. The largest known star is not necessarily the largest star that exists. It is the largest that has been identified and interpreted with present observation. Other extreme stars may remain hidden by dust, distance, crowding, or the incompleteness of surveys. Future measurements may refine current estimates or alter the ranking. The phrase known star therefore matters. It places the object within human knowledge rather than outside it. Astronomy speaks not of final possession, but of the best current understanding of a vast and only partly revealed universe. In the end, the meaning of the largest known star lies in the union of limit and transience. It shows how far a star can expand. It shows how unstable such greatness becomes. It shows how the deepest workings of fusion and gravity can create an outer body of astonishing scale, and then slowly withdraw the conditions that sustain it. A red supergiant such as Stephenson 218 is therefore a record, a process, and a warning from nature all at once. It is a record of observed size, a process of late stellar evolution, and a reminder that the most expanded forms in the universe are also among the least permanent. Seen in this final inward light, the largest known star is no longer only a distant red supergiant in an obscured cluster. It is a measure of what matter under gravity can briefly achieve. It is a luminous boundary in stellar evolution. It is a source of future galactic material. and it is one of the clearest examples of how the universe joins grandeur to impermanence, allowing immense forms to exist for a while, to illuminate their surroundings, and then to pass their substance onward into the next generation of cosmic history. The largest known star begins as a point of light in the night sky and becomes, through careful study, one of the most expansive bodies recognized in the galaxy. Its path leads from the Milky Way, through dust-rich regions and hidden clusters, into the outer glow of a red supergiant, then inward through atmosphere, surface motion, layered burning, and the dense contracting core. At every depth, the star reveals a different kind of truth. Its immense radius belongs to the visible outer envelope. Its red light belongs to a cool, extended surface. Its instability belongs to weak gravity in the outer layers and to the restless transport of heat from below. Its future belongs to the core, where gravity and nuclear change continue their long inward work. Stevenson. 218 stands as a leading candidate for the largest known star, though the exact record depends on measurement and remains open to refinement. That uncertainty does not diminish the star. It places it properly within science, where observation and caution move together. What is clear is that stars can expand to extraordinary scales, far beyond ordinary intuition, while remaining temporary forms in a changing universe. Such a star is not large in the manner of a mountain or a planet. It is large as a luminous envelope of gas, thin in its outer reach, unstable at its edge, and sustained by deep processes that cannot last forever. Even the greatest known stellar expansion is part of a brief late chapter. The star loses matter, enriches surrounding space, and approaches the limits of support in its core. Its immensity is real, but so is its impermanence. In that calm fact, the largest known star becomes easier to understand. It is not a monument that endures unchanged. It is a passing state of matter under gravity, briefly stretched to an extreme, glowing softly across a vast radius before giving way to the next stage of cosmic change.